their famous package now, the leading package for hypergraphs.
Yes. Thank you. Thank you very much, Pavel. Yes, my name is Cliff Joslyn. I am the Chief Knowledge Scientist, is what they call me, as well as the lead for Mathematics of Data Science. I'm at the Pacific Northwest National Laboratory in Seattle, Washington. I'm here with Auden Myers, my colleague from the lab, although he lives in Michigan. We're that way these days. And I want to thank Pavel and all of the organizers for the opportunity here. We were here last week as well for the Hypergraph workshop, different collection of PNL people. And it's been really great. We've been integrating with this particular community now for a number of years and really recognizing WOW and the related organizations as really representing sort of the high ground for complex network analysis and hypergraph analytics in our case. Yes, I understand that we're being recorded. Okay, interesting. You never know what you're going to see here. Okay, so like I say, I want to recognize the principal contributors to at least the slides that I'm presenting here. I had a different talk last week. Sinan Aksoy, Tob Hagee, Brenda Pergastis, Emily Purvine. Brenda was here last week, as well as a very long cast of characters. We've been working in this space now for a long time. We have a number of contributors back at PNL as well as elsewhere around the community. Today, I'm going to begin with some advertising for some of our programs for another talk we have upcoming today, and then get a bit into the foundations of graphs and hypergraphs. I'll be somewhat mathematical. I'm going to be gentle, but also a bit mathematical as we go. And I've got, if the gremlin God's willing, I've got a HNX demo that I'll be doing in parallel with the slides, our HyperNetX platform. I'll talk some about the relational mathematics underpinning hypergraphs, data sources, and then some of the properties that I think are important as for anybody who's approaching complex network analysis from this perspective. Duality, width of blocks, nesting and ordered relations that are inherent in hypergraphs, how we handle attributes and properties, some of the topological approaches, and then we'll conclude with some what we call S-network analyses. S is a free parameter, which is basically a parameter that controls the width or the strength of different sorts of path connections, which can only be modeled in hypergraphs and can't be done in regular networks. So a little bit about PNL. We've been working in this space now for, getting many years now, almost getting on a decade. Kind of a dual program. On the one hand, hypergraphs for hypernetwork science, and then dually with that, computational topology and multidimensional data analysis. We'll have a little bit of the computational topology here, not very much, but it occupies, we come from the perspective that high order networks and computational topology is basically one field, and there's reasons for that, and there are different approaches, and different people might disagree with that, but for us that makes a lot of sense. So if there are those here that want to carry on with me later on about that aspect, and also Auden's talk this afternoon will be in that space as well. We're talking about HyperNetX. We're very proud to announce the 2.0 release. We also have this kind of, we don't call it deprecated, we don't call it depreciated, we call it completed. The Chapel Hypergraph library, which is a high-performance hypergraph package written in the experimental data parallel language Chapel. We, as an applied science U.S. government research laboratory, we also work on tons of applications. Cyber open source intelligence, computational virology. I have a project, believe it or not, in computational chemistry involving these methods, scientometrics and related things.
Maybe you should click on this guide.
I don't think I know how to or can. I don't see it on either of these.
Maybe if you go your mouse directly.
No, this is not me. I deny any responsibility for this. Okay. Advertising. This is Auden's talk at 3:30. Come to it. Look at that. Isn't that great? Look at that. Come to this. HyperNetX 2.0. So we've been working with this package now for a number of years. HNX, it is implicitly, if not explicitly, modeled after NetworkX, the world famous Python package for graph modeling. The 2.0 release includes a slew of exciting new things. Oh my gosh, look at that laundry list. This is Brenda Pergastis's work primarily, with a team involving also Madeline Shapiro and Mark Bonicello. Oh my gosh, clustering modularity, Laplacian clustering, generative models, topological approaches, all this S-network stuff we've been talking about. A lot of interesting engineering innovations in 2.0 under the hood related to, we're now sort of based in pandas data frames throughout, which gives us a lot of utility for handling data attributes. This is the homepage for HNX 2.0. And we've got a lot of tutorials. There's a little write-up I did on general introduction to hypergraph mathematics, sort of paralleling what we're showing here, and a range of different tutorials as well in different areas that are available there. This is, God's willing, this demo will continue to run. I'm actually port tunneling out to my mainframes in Richland, Washington right now. So it's kind of held together tentatively. We'll hope that it keeps going here through the morning. Yes. Better? Yeah. Excellent. So a bunch of stuff. It's your standard pip installs, and I'll come back here and we'll come back over here in a moment and show some of the different methods that we have available and some examples. We're also very proud of our visualization widget, we call it, for lack of a better word. It gives an interactive dynamic display of small to medium-sized hypergraphs in both, as you can see, both bipartite and Euler diagram form. It also supports duality and a bunch of statistical things as well. And I'll be showing this off as we go through the discussion this morning. Our overall orientation to this overall scientific program, we sort of feel like we can characterize it this way. Obviously, graphs and networks are the foundation for everything in this space and broadly in the world of network science. But as soon as you start to allow for more than two interacting elements, now you're into the world of hypergraphs. And if you also additionally support if you attend to the included edges within your hypergraph and take seriously the idea that there are equivalence classes of hypergraphs according to the inclusivity of the edges, you end up with this idea of an abstract simplicial complex, which probably a number of people have heard about in the complex network space. This is a topological structure, although we call this hypernetwork science now, is this mixture of graphs, hypergraphs, and dealing with these abstract simplicial complexes. As I said, however, this abstract simplicial complex is in fact a topological structure. It implies a topological space. It's a finite topology. And this opens up the world to the world of computational topology in terms of persistent homology, as it's called, topological data analysis, as it's also called. We go even further than that. When we have data structures that are sitting on your hypergraph as well, that's an opportunity to play even more sophisticated games in the computational topology space involving topological sheaves and pre-sheaf models. We've been working a fair amount in that space as well. And I don't have anything on sheaves in this particular talk, but for those interested, I can carry on afterwards. And we call all of this together computational topology. Now this little notice is on me, and I will close that one. Okay. Very good. And there's a reference there up to the top where we sort of introduce these ideas. All right, graphs and networks. I don't need to talk to this group about graphs and networks. Hypergraphs, although notice how I say this. Graphs natively provide a mathematical model of data focused on uniform two-way relationships among one variable, right? So think of the vertices as my graph as representing a single kind of thing that I'm measuring, and then I can look at the pairwise relationships amongst that one thing. When I talk about hypergraphs, I frequently think about it this way. Hypergraphs natively provide a mathematical model of data focused on non-uniform, multi-way relations between two variables. That is, the vertices and the edges, the hyperedges in a hypergraph represent a distinct variable, and I will show you how that works. But in both cases, we're asking certain kinds of questions about connectivity, clustering, multi-way relationships, etc. Here we have in graphs, we have vertices and edges. Here we have vertices and hyperedges. I've been using this slide for many years. This is a little example. If I've got a little data structure here about how authors are related to papers, I got a bunch of papers with different authors on them, right? Typically, what we would do in a network science approach is to build a little adjacency matrix as to which authors are connected to which authors and the fact that they've written a paper together, and build a little graph. And we'll notice that everybody's written a paper together except for Davis and Bailey, so it's not a fork-leak. Now, if you just look at this and you say, what about the multi-way relationships? As far as you can tell from that graph, it's as if Andrews, Davis, and Carter did a thing together, and Andrews, Bailey, and Carter did a thing together. Those are the maximal cliques of that graph, right? But of course, we know that's not actually the case. What's actually the case is this hypergraph representation of the actual multi-way relationships that are present on that data frame up in the top left. So the hypergraph representation is the proper representation representing which papers had precisely which authors, noting that I can have papers that have a single author. I can have papers that have 2 authors, 3 authors, etc. So this is a fundamental motivation for the uninitiated into the significance of a hypergraph approach, especially when it comes to relational data. Fundamental definitions. We've got a set of vertices and we've got a family of hyperedges that is sometimes thought of as a subset or as a set system. In fact, that's an indexed family because I can actually have repeats. I'm not actually showing that in the slide. I should, but I'm not. So it's a set of family of subsets like this. In principle, I can have repeats in that list, so it shouldn't be a set. So it's a multi-set system. Sometimes I use compressed set notation just for convenience. And sometimes we can actually go through and label the individual subsets that are present there. And that's the indexing that it supports the indexed family, allowing for the repeats. Typically, what we also do is represent this as an incidence matrix of which vertices are included in which hyperedges, or as an Euler diagram where we surround the vertices of the hyperedges with these blobs. We also like to use this idea, which is a simplicial diagram. For those of you who do the computational topology and all that, is basically an abstract simplicial complex that has been adorned with the numbers indicating the precise hyperedges that are also actually present. Notice that I've got the AD hyperedge as a edge that is listed. It's included here, but the DC edge does not have a number because the DC pair does not actually occur in the hypergraph itself. These are also represented as bipartite graphs where I have the vertices on the left and the hyperedges on the right, and I'm showing that in 2 different forms. The first is the classic form here where for layout purposes the 2 parts are distinguished, but of course that doesn't really work for bipartite graphs of any size where you frequently want to let the layout relax and integrate the 2 different metatypes of nodes that way. All right, so we're seeing that these different relationships, the set system, the multi-set system, if you will, the incidence matrix, the bipartite graphs, simplicial diagrams, Euler diagrams, all of these are related together in particular ways. I do want to say here in prep for the next slide that axioms matter. So whether or not you represent, so first of all, singletons being different from vertices, the presence of isolated edges, empty edges, multi-edges, self-vertices, and self-loops are all part of the story of when it really takes to ground these things formally at the mathematical level. We have been working in category theory along these lines. Categorification of the hypergraph space has been attempted multiple times. We think we've got our hands on it as well. And we can talk about a functorial theorem that actually shows the functorial equivalence, the categorical equivalence between the category binary relations, those incidence matrices as basically just binary relations, finite binary relations on finite sets. The hypergraphs as we define them in terms of incidence relations or incidence functions, bipartite graphs as we've just shown, and finally hypergraphs themselves as set systems, as multi-set systems. So mostly to make sure that we've got our feet under us securely, we've gone ahead and shown these categorical loads. We haven't published it because it's not really worthy of being published, but we wanted there are enough definitions out there in the literature relating these things. We wanted to make sure that we really understood, not just from the perspective of the bijective relations amongst the objects, but also carrying the morphisms through, as we do in category theory. Here's a little précis on just the relation between graphs and hypergraphs. First of all, critical to notice, every graph is a hypergraph. Yay! So hypergraphs explicitly generalize graphs in that every graph is a 2 uniform hypergraph. That said, we can look at a little example graph on the left, a little example hypergraph on the right. Notice I'm showing an incidence matrix for each of them because, of course, graphs also have incidence matrices, right? Notice that's not an adjacency matrix. That has different thing on the rows and the columns. There are vertices on the rows, and it's the edges that are on the columns for both of these. What you'll notice, however, is that for the graph, the incidence matrix has always exactly, precisely 2 check marks in each column because those are all graph edges. That's a 2 uniform hypergraph. Whereas the incidence matrix for my proper hypergraph is arbitrary. I can have as many checkboxes in each column as I want. On that basis, we think of graphs as being a subset of v squared as opposed to the hypergraph being a subset of 2 to the v. It's kind of an exponential object. Connections have length as well as width. These are much more complex objects. However, they losslessly can represent relational data, but they can get large, possibly exponential. But they also support these higher order properties that we care about. So graph theory, network science collapses out as a special case of hypernetwork science. So why not hypergraphs all along, right? I get this question all the time. After all, graphs are just special to uniform hypergraphs, and hypergraph data are ubiquitous. Set-based observations, bipartite graphs, relational tables, maximal cliques of graphs, reified RDF, for anybody out there who does that. We had somebody last week who did, are you here? No. Metric spaces yield VR complexes and related things. These things are everywhere, but most graph treatments of complex data flatten to force binary relations. Why is that? Despite the fact there are many known hypergraph results, some prior application attempts, need for new methods, need to integrate all these into a coherent methodology, which is what we're doing. Why is this? Well, obviously the community has difficulty with both the mathematical, conceptual, and data complexity of hypergraphs relative to graphs. Hypergraphs in general can approach exponential sized objects as opposed to quadratic sized objects. And that's throughout this literature, throughout this field. That said, it's time. We're taking up the challenge. There, in fact, is a burgeoning movement in network science in this space. This slide is actually getting a little bit old by now. I built this slide like 2 years ago, showing all these cutting edge publications from really high powered people. I should update it, but this idea of simplicial modeling and hypergraph modeling is really taking off. And there's an awful lot of work these days in this space. A lot of it is coming from the physics modelers, the phys-rev-e crowd, as I like to call them, doing dynamics on high order relationships. High order networks is another sort of turn of phrase that's being used, complex networks, et cetera, and related things. We like to think we're at the vanguard of this as well. I want to give another little perspective. So, as I've been saying, we're able to ground hypergraph models from multiple different sources. And my point of departure in all of this, and this is a bit in contradistinction to the current movement towards towards the statistical modeling and the AI movement around what's called unstructured data, text, images, signals, and learning systems against them. I'm grounded in structured data. And so structured data comes typically as categorical variables, not continuous variables, and in these kinds of multi-relational forms, like a pandas data frame, as an example. Lots of the domains that we work with can be structured as these kind of multi-relational systems. So in cybersecurity, domains against IP addresses, against MAC addresses, against malware types. You get these big data cubes, if you will, full of these multiple columns. In social networks, people against groups. In bibliometrics, authors against papers. CBP, that's in the United States, the Customs and Border Protection folks have airline passengers against border crossings, against cargo shipments. And you get these full kind of matrices along these lines. And the point is that these multi-relational systems yield to network science representations rather straightforwardly. We've already been seeing how if I've got two variables, I just form this kind of an incidence matrix. This is a many-many relation. In this case, we're showing IPs against ports. And in fact, every IP is associated with many ports. And every port is associated with many IPs. This is not a functional relationship, right? This is a many-many, not a one-to-many or many-to-one relationship. IPs against domains. And I can add in additional axes as well, the type of service, FTP versus HTTP, the kind of malware, and I get these kinds of relational data cubes. In that context, relational structures arise naturally. So a graph in this context is a self-relation against one variable. Remember, I said uniform binary relations amongst one type of variable. So I get IPs against IPs and I build an IP graph, or I get domains against domains and I build a domain graph, right? These are dual graphs that are available from that one relational structure. While a hypergraph is going to be a binary relation on that same structure. I'm going to have domains as sets of IPs. I'm going to have IPs as sets of domains to form the hypergraph. One could ask then, great, you said it's a multi-relational structure. Well, if I've got these two dimensions, but I've got a whole lot more columns up in my data frame, and in fact, lots of different sorts of tensor structures are also available. I could take any 3 columns from the data frame and produce a 3-way tensor. I could take a different set of 3 columns and get a different 3 tensor. All of these relational structures, they chain into each other and they overlap with each other in interesting ways. The combinatorics of these structures are really fascinating. But these kinds of tensor structures are always available. Okay, we've made some progress at PNNL on this sort of broader perspective of multi-relational analysis yielding into these kinds of network science and hyper-network science approaches. I just want to show a little bit more in detail how this works for two variables specifically. So I got graphs, hypergraphs, and relations. I start off with the idea of a binary relation. Notice again, that's an incidence matrix, not an adjacency matrix. It's two different things against each other, the vertices against the hyperedges in my incidence matrix I. We know that we can represent that also as a corresponding bipartite graph. Those are bijective as objects, and now we've shown that they're functorial as categories. From that, as we said, I can extract a graph on the rows showing all the pairwise relationships. This is in fact a weighted graph because it's showing which combinations of vertices are held in common between the different edges. AD occur twice, as you can see. And I formed that linear algebraically, so that's just IIT minus D. So the standard building a Laplacian sort of structure for that, minus that diagonal. Of course, dually, I can get a graph on the columns. That is all the pairwise relationships. And it's the dual of that. Instead of IIT, it's ITI. But what I really want to do to capture the full complexity is to form this hypergraph on the rows. We call this the primal for no good reason. It just sort of comes to us this way. And that is my incidence matrix now is considered a subset of V cross E. And the dual hypergraph is also available. We call this the dual because we called the other one the primal, just because we have to call something something. This dual is H star as opposed to H. And notice it's working on the transpose of the incidence matrix as a subset of E cross V. So this is basically how it works for basically everything that we're going to be dealing with here. In that context, now I can go back and reinterpret these graphs in a hypergraph theoretical way. This graph over on the side here on rows is called the two section of the primal. It's also called the clique expansion. It's also called the underlying graph. You see all these terms in the literature, and it's the most common thing you do with a hypergraph is to collapse it down to this underlying graph and then do graph analysis on it. And sometimes that's okay, but not always. In the dual form, this line graph of in the dual form, we recover what's called the line graph. So the line graph of the primal is the two section of the dual. And so between the line graph and the two section, you're capturing all those pairwise relationships. Like we said, it's common to reduce your hypergraph down to those graph relations, but we like to do better than that when we can. Very good. So this is basically how a standard binary relation works in this context. And this is how we know how we're going to be able to get data into these structures. So a little slide here on how data come for hypergraphs. First of all, set value data. I've got a collection of groups. I actually measure things in groups. If you have a sensor that reads off in groups and gives you a variable length list effectively, right? So it's not a traditional sensor that's reading off single numbers or fat vectors that are full of the same kind of information over and over again, rather variable length lists. So I've got the supervisors, those with brown eyes, the females, and the surgeons. And I can put that into this relational form. I've now formed an incidence matrix, basically Boolean attributes. Entities on the rows are indicated as having specific attributes or properties on the columns. This is a typical way, most typical way, but you can also sometimes get data coming to you as joint relationships around the pairs. In this case, around the pairs of the IPs and the domain names, we're given what's associated with something else. So the incidence matrix might come to you just as it is. Also, of course, we can get numerical data in our data frames. In this case, I'm showing the relative expressivity of certain genes under certain conditions. Under those conditions, you just do some kind of filtering process. In this case, I'm filtering to the positives to return a Boolean attribute. So in all of these cases, we end up with a Boolean incidence matrix and go ahead to form the hypergraphs on that basis. So that's just 3 examples. By the way, the asterisk up there, that's to remind me to flip over to the HNX. So if I flash past one of if you see the 3 stars up there and I don't go to the notebook, please stop me because I'm just being foolish. Okay, so this is a little demonstration how some of these things work in HNX. For these purposes, we're simply establishing, here I'm just stashing some positional variables that I'll use for visualizations. Here's this is a dictionary of some scenes and characters from Les Miserables, the famous novel, full of characters and full of scenes. And Don Knuth, believe it or not, actually went through and got detailed analysis of every character appearing on like every sub-page of every sub-scene. And there's this big hierarchy that goes up to the giant volumes of this monster novel. And it's a very nice relational structure that we've been using for demonstration purposes for a long time. In this case, so Jean Valjean is the abbreviation for that character. Each of the characters gets a 2-letter abbreviation. And then we've got scenes 0 through 7 in which they occurred. Ooh, let's see. Let me try to actually run it. Let's see if it's going to go. Yes. And so then we're able to plot out. This is the default drawing utility, but it's using the coordinates above because we know what a good layout is, and so we stored the coordinates. And there you go. We've got our, this is the Euler diagram of this hypergraph showing the various scenes labeled 0 through 7 together with the constituents. We then have our famous hypergraph drawing widget, which we have here. And since Bogle made me zoom in, now it's, yeah, we're going to zoom back out just a little bit. So I think it's safe. Do I dare do it? Oh, good Lord. No, I'm not going to do it. I was going to re-invoke it to get a fresh layout. It seems okay. Okay, we're going to do it. Yes, it worked. Okay, so I'm tethered to my mainframes in the United States over VPN and through port forwarding and all sorts of things, so it's dangerous. So here, and you saw that it sort of jiggled when you made the layout. We can take any of these vertices and move them around. I can grab a whole edge and move it around. Things become pinned once you stick them, and I can unpin them all and let them relax back to the normal way that I want to do it. I've got properties on vertices. I've got properties on edges, or I've got distributional properties. So the edge sizes are here. I can sort up and down by edge size. I can color by edge size. I can color, okay, get out the glasses. In this case, I want to color by edge size, for example. Oh, I can increase the font size. That's important. They gave me that just recently. I got lots of different palettes that I could use. I could switch over to a different palette. I'm not seeing as the sort by weight by edge size. There we are. So there's a weight in here. Sorry, I'm not. I want to. Do you remember how to weight or color by edge size? That should be down here. It's not here. Well, and then there should be no degree here as well. I probably got to turn. This is a new version. I'm not as familiar with it. I got to probably turn these degrees into weights somehow. Would be my expectation. All right. Well, trust me, it's doable in principle. The other thing I can do is I can expand it to full view, and I can also show the dual at the same time. We'll talk about the dual in a minute, but this is the dual form of these two together in the same place. So in the dual form, I've got vertices for the edges, and I've got edges for the vertices. Just flip them back and forth. And in fact, they're showing the same information. And you'll note they have actually the same topological structure, and that's by Dowker's theorem. I've got an open loop here, and I got an open loop here as well. All right, turn that back off. Get out of here. Oh. No, there. I want you to go back to that. Thank you very much. So we'll get back in here in a little bit to show some other things. Oh, right. Now, there's different forms. So what I might want to do is just go through and list, instead of the basic data as I've got here, I just want to make a list of all of the contents of each of the hyperedges. I can form a data frame from that. So I've just got a pandas input instead of a Python input, or I can go to NumPy and make a NumPy array. And in all of these cases, this cell just shows creating a hypergraph from any of those input sources and verifying that they all show the same visualization. So just different ways, fluidity of coming in from these different data structures, arrays, data frames, lists, and dictionaries, which is very nice. And of course, all that also comes off of the file system if you wanted it to. We've got a variety of basic information and statistical information about degree distributions and related things that are available. And we've also got a nice state dictionary, which means that if you're calculating complicated things, you'll be able to store them locally, persist them at least for the duration of your session, which can help because some of these calculations can be burdensome. Okay, back to watching my time and getting back to the story. So As we just said, hypergraphs come in these dual pairs. This is really interesting because I always try to emphasize this when I'm working with hypergraph data of any form. There is not one hypergraph. There is always a dual. Now, depending upon the semantics of your problem and where the data come from and what you're trying to deal with, the dual may or may not be meaningful for you. It may not be important for you, but it's always there as a mathematical matter. And you can see how it's done. Basically, either, when I think about it as a bipartite form, or I think about it as the incidence matrix, that dual is always available. I can always transpose the incidence matrix. I can always basically flip the two sides of the bipartite structure. So what I do is I make a new structure where I now add a vertex for every edge and an edge for every vertex. Ooh, fancy. And separate them out, and you can see we've got that dual form that's available here. So it's proper to consider that hypergraphs always come in dual pairs. Oh, now wait a minute. I said that every graph's a hypergraph, right? So if every graph's a hypergraph, it follows that a graph actually comes in a dual pair as well, right? Well, all graphs also have duals. In almost all cases, the dual of a graph is a hypergraph, a proper hypergraph, not a graph. In fact, there's only if that graph is a collection of cycles is itself dual. Basically, it's a two uniform hypergraph on the input, and the self form of that would be a, not two uniform, but two regular. A two regular hypergraph on the other side. A two regular hypergraph is one where every vertex is in two edges, as opposed to every edge having two vertices. So there you go. And back on, I got the stars here. So back here, similarly, I can form the dual of the hypergraph and then show it there. And in fact, we already saw it on the widget as well. Let's go back and remind ourselves about that. So I go to full screen view and then split the dual. And you can see that there is literally, and notice this kind of multiplicity thing here. Notice that CN, CC, and BR really can't be distinguished except for their labels. They're all playing the same functional role. In the incidence matrix, that means I got 3 duplicate rows. Over here, that turns into these concentric circles where I've got this is a multi-hypergraph, where I've got multi-edges that are surrounding the same collection of vertices. So that's how that shows up in the dual. I got the Zoom interacting with this, so that's part of the fun. I think that's it for that. Yes, okay. So I am watching my time. What I really want to try to do with the rest of the talk is to walk through some of the most important properties of hypergraphs when you're working with hypergraphs. In some cases, this is in interaction with underlying graph structures. There are a lot of underlying graph structures. We've already talked about the 2-section and the line graph. We've talked about the bipartite graph, which is a graph, although it can get subtle. You got to be careful. There's all these different structures running around. They're all related to each other in important ways, and it's easy to get, if we in our meetings, we say the node, the vertex. Wait, which node? What are you talking about? What graph structure are you actually in? So it can get a little confusing. Nonetheless, we're going to soldier on here. Some of the important properties of hypergraphs when we're working with them. Walks in hypergraphs have length and width. So an S-walk is what we call a structure which is a sequence of hyperedges where the intersection between them is of a minimum size of at least S. So in a graph, I can talk about a graph path. In this case, it's of length 2. Does anybody agree with me that that is a path of length 2? Well, the trick, of course, is that number 1, I'm going edgewise, and number 2, I'm going origin 0. So it's I can label my edges as edge 1, edge 0, edge 1, and edge 2. And of course, I can represent that, of course, as a uniform hypergraph as well. A 2 uniform hypergraph is equivalent to that graph up there. As opposed to here on the right, I'm showing 2 different hypergraph paths. They're also both of length 2, but the one on the left has a width, if you will, or an S value of 1, because I've got exactly 1 node at the intersection. Here I've got an intersection of 3. Here I've got an intersection of 4. Therefore, I take the minimum and call that a 3 walk. A 3 walk of length 2 on the right, as opposed to a 1 walk of length 2 over on the left. So that's pretty neat. I've now got to think about 2 factors, not just 1, when I'm doing my walks. I'm going to increase this slide a little bit later also and talk. I should have another slide. I don't, so I'll just tell you. An important property here also is, in a graph, I can make a walk, which is just a collection of vertices, right? If I say vertex, 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 that establishes a walk. That vertex walk also establishes an edge walk, edge, 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 which are exactly those edges that connect exactly those vertices. Talking about a simple graph now. Similarly, an alternating sequence, vertex, edge, vertex, edge, vertex, edge, all one object. It's not the case in hypergraphs. So in hypergraphs, the edge walk does not determine a vertex walk, and an alternating walk, vertex, edge, determines both an edge walk and a vertex walk, but not the other way around. So this whole idea of taking walks and treating them with width extends generally. First of all, we can define now a S distance. That is the minimum size, the minimum walk length of a S width between two vertices is a distance, which is obviously a generalization of graph distance. And that now opens up the idea of S components, S centrality, S diameters, S motifs, S clustering coefficients, etc. The whole world of network science now opens up to expand in this way, which is very nice. So paths have length and width. Critical to that idea is also that hyperedges can be nested, which is a thing that cannot happen in graphs. So in a graph, I'm showing two incident edges and I'm showing two disjoint edges, right? Edge A and edge B are incident up top and they're disjoint down below. In all cases, A and B are of size 2. Remember, there's a 2 uniform hypergraph. And I'm using the triple equal sign there. They're precisely necessarily equal to 2. I can think about the intersection and the size of the intersection of these edges. So the intersection is a single vertex V and the size is necessarily 1 in the case of incidence edges, and they're disjoint, and so the intersection of size 0 in the disjoint case. So far, very, very straightforward. All right, let's think about this in hypergraphs now. I've got two hyperedges. Notice they have different sizes. I've got edge A of size 3, edge B of size 4, and I'm showing the incidence case. Now the incidence between them is a quantitative thing. In this case, I'm showing that, the way the slide builds is, let me do it the way the slide builds. We can also talk about the intersection and the size of the intersection. In the case of the disjoint edges, of course, it's the same. They're disjoint and the intersection is 0. But in the case of the incident edges, I have a collection of vertices which is of size greater than or equal to 1. So this is the strict generalization. But notice the big white spot at the bottom of the slide. What's coming? There's an additional case, right, for hyperedges in that one can be contained in the other. Now, the intersection is just the first one that's contained in the second one, and the size of the intersection is just the size of that set. And of course, we have the NA case in the case of the graph. This cannot happen in graphs. So attending to this sets you up for really understanding how to work with these structures. Because of that, these things have a kind of inclusivity parameter. For those of you who were here last week, Nicholas Landry was talking about this aspect as well. So we start with this hypergraph, which we can show as the Euler diagram or the simplicial diagram. And one thing we notice is that there's a partial order that's related to this, which is the edge order, right? Edge 3 is contained in edge 1, is contained in edge 2. And then I got 4 and 5 kind of hanging out to the side there because they're not included one way or the other. That's a legitimate partial order. We call the maximal edges 2, 4, and 5, we call them toplexes. And I can measure the inclusivity as the number of, is that wrong? Oh, sorry, as the number of included edges, not toplexes, relative to the total number of edges. So there's 2 edges that are not toplexes out of 5. So we measure the inclusivity there as 2/5. In the case of what's called a simple hypergraph where they're all toplexes, in this case, I'm showing that by actually eliminating those 2 included edges, retaining only the toplexes. Now, of course, my inclusivity has dropped to 0, and notice my partial order is still there, although it's this weird vestigial little thing. Technically, that's just a single antichain in the partial order. All right, so I can remove all the included edges, but the other way, I can also include all the possible included edges to form a structure we call the abstract simplicial complex, which is the entryway to the computational topology world, basically. So in this case, I'm adding them all in. I now get a very rich ordered structure there on the lower right. It's literally the union of 2 Boolean cubes, or 3 Boolean cubes in this case. So a 3 cube under 2, a 2 cube under 4, and a 2 cube under 5, modulo the bottom, which should be included in there, the empty set as well. So that's as much inclusivity as I can have, and in this case, it maxes out at 710. You never really get to 1. So all of these share the same topological structure, which is determined by the toplexes. And in fact, there's a bijection between the reduction and the closure. So the abstract simplicial complex and the collection of toplexes are in bijection. These are all equivalent. So this is a whole equivalence class of hypergraphs relative to that top and that bottom. And that's what carries the topological properties of for simplicial homology. I got my 3 stars, so I'm going to go flip over and show that we've got, I didn't want to do that. Excuse me, I want to be down here. So we can calculate the toplexes, and now I'm showing just the toplexes for that dual hypergraph over there. And you can see it thins out the structure, and the included edges sort of imply the upper edges for topological purposes, and so we can get away with being much more slimmed down that way. A little bit out of sequence, but just the way this notebook happens to be built, we have only now am I showing the bipartite graph structure. Also, our friend Nicholas Landry has a package called XGI, which is similar. We're able to import that and show the bipartite graph in that as well. We also saw the bipartite graph here in the widget. So I can show the bipartite graph form this way, and now instead of the hyperedge being a rubber band, the hyperedge is now a node of a different metatype. So I've got the squares showing the hyperedges and the circles showing the hyper nodes, the vertices. And you can see the inherent duality in the structure here as well. One could just as easily say it's the circles that are the hyperedges that are collections of the squares. Okay. What was that? Did you see that yellow flash by? Okay, I don't know what's going on. A little bit more about ordering. This is some new work that we started in on, which we think is really sexy and cool, and it's been, I'll just show a couple of slides on it. Again, watching my time. So as we noted, hypergraphs have this inherent order. I'm showing that same ordered structure a little bit differently notated on the right. Here I'm using a little notation that's, we're calling it Galois notation. It's a combination of, so the colon separates a collection of vertices on the left and a collection of hyperedges on the right. You can think of it as a union of vertices on the left and an intersection of edges on the right. So for example, this edge AD here is the intersection of 1 and 2, which is just 1, and it's the union of A and D, because it is. So that's just a way to notate this. But, and I need to modify this slide. Imagine I've got 2 hyperedges that are disjoint. Okay, now imagine that I got 2 hyperedges that are incident, that have a non-empty intersection. From the order perspective, those have exactly the same partial order, right? Because neither is included in the other. But in the second case where there's a proper intersection between them, I really care about that intersection. It tells all the story about that hypergraph is told by the fact that there's this positive intersection. And in fact, that intersection is included in both of the hyperedges. So what I really want to do is go beyond the hypergraph as it's handed to me and form what we call the intersection complex. I recursively form all the intersections of my hyperedges, and then I draw the order relation for that. So A:124 is the singleton A, which is the intersection of 1 and 2 and 4. Etc. So all of these are played out that way. We've got a beautiful theorem that says that this intersection complex is bijective to what's called the concept lattice in formal concept analysis, which is a kind of relational mathematics mixed with order theory that's been out there for about 20 years. And we're working on questions about how hypergraph operations are mirrored in the corresponding concept lattice. We're also working with another structure called a Dowker complex. Notice in the intersection complex, I'm forming intersections. In the Dowker complex, what I'm forming are these abstract simplicial complexes. I'm closing down by subset. So that lattice over there in the center, this lattice here, is now showing not just the intersections, but also all the possible included subedges. And we're working on some very nice theorems there that show there's a lot of functorial and categorical things that you can move between these different categories. And there's actually a sheaf model that underlies that as well. It's a sheaf of abstract simplicial complexes. I'm in the Fields Institute, so I can say that, right? Okay. Cool. And here's another little example. Forget the numbers, the weights. I pulled this graphic from other purposes where I was using weights on these structures as well. But look at this little hypergraph here. In red, I'm showing the toplexes. or sorry, in red I'm showing the actual edges that are in the hypergraph. So like 1, 2 is there as an included edge inside 1, 2, 4, 5. And then this is the rest of the intersection complex, and this is the corresponding concept lattice. So these are all bijective. So in the same way that the hypergraph is equivalent to its incidence matrix, is equivalent to its bipartite graph, it's also equivalent to this ordered structure. That's true bijectively, it's also true functorially. Beautiful. Okay, what I'm going to close on with, I'm going to speed it up a little bit and just mention a couple of things in passing. First is properties. So we've been talking so far about kind of basic hypergraphs. Notice I haven't talked about directed hypergraphs or ordered hypergraphs. Those are out there, they're real things. We sort of bundle them up together with attributed hypergraphs. We're motivated a lot by ideas in sort of semantic graph theory, that if I want to represent high order relations, like Adam gave the book to Clarice, which is not a two-way relationship, but a three-way relationship, that I want to be using an ordered simplex in order to be able to do that, labeled simplex, instead of these other sorts of graph strategies around reification, subgraph identity. There's lots of little tricks that network scientists use to represent this kind of high order information, and we think we can do it that way. As I mentioned, ordered and directed hypergraphs are a thing. In graph theory, ordered graphs and directed graphs are the same thing. Every edge, you say, if we have a directed graph, then A points to B. We say that A is the source and B is the sink. That means that there's a bisection between the thing on the left and the thing on the right, which means there's also an ordering relation. The thing on the left comes first, the thing on the right comes second. So order and direction are the same in graphs. They are not in hypergraphs. So in hypergraphs, in order to establish an ordered edge, I have to basically give a total order or a permutation to the members of the hyperedge, whereas for a directed hypergraph, I do a bisection, and I say this group of vertices are the input and this group of vertices are the output. There's a lot of literature in directed hypergraphs. There's very little literature in ordered hypergraphs. As I mentioned, we approach all of that from a generic position of property hypergraphs. So we've got our vertices, our edges, and now I'm showing just a list of incidence pairs as forming my hypergraph. And we simply establish 3 property functions, one on vertices, one on edges, and one on incidences. Represent those properties in various ways. They can be all sorts of data types, and they can have multiple attributes, they work in the dual, all this kind of stuff. So we've built up sort of the mathematical machinery we need around this, and we can actually define ordered and directed hypergraphs using combinations of these attributes, Boolean attributes. Imagine a Boolean attribute sitting on a vertex to decide whether or not it's on the input or the output. Another thing I want to mention is this idea of incidence properties. So not only do I have properties on the rows of this matrix and the columns of this matrix, I can also have properties on the cells of this matrix. This is actually very important. This is important conceptually, it's important methodologically because we get data that comes that way, but also it's important mathematically because there's a theorem from Chitra that says that if you're dealing with a weighted graph structure, in particular you're dealing with a weighted graph structure in order to provide a random walk over your hypergraph so you can build a Laplacian and do clustering, that if you don't have weights on the cells, if you only have weights on the rows or on the columns, you're almost always going to collapse that random walk down to a random walk on the underlying graph, the clique expansion, the 2 section, or the line graph. So it's come to us from multiple directions, this need to have these incidence properties as well. Topological properties. I'm not going to take really much of time here at all for this, but as I think we can appreciate, hypergraphs present as multidimensional structures glued together. They're topological complexes. 0-dimensional being the points, 1-dimensional being the edges. That gets you up to graphs, but with hypergraphs, you can now in 2-dimensional faces, 3-dimensional solids, etc., all the way up. These form these structures called abstract simplicial complexes, as we've been discussing, which have these Betty sequences or Betty signatures. I can measure the number of 1-dimensional holes, 2-dimensional holes, 0-dimensional holes. There's 0-dimensional holes. 0-dimensional holes are connected components. So it's very natural sort of development. And we do a lot of that stuff. I think I had did I have a star to bring me back? There's a bunch of, so the rest of this deck is showing how we do properties. Where am I? So because of the pandas base, we can now build out pandas data frames that have all these properties. In this case, I'm just showing this kind of mock-up example, again, within Les Miserables. And on that basis, we can bring those properties now through the pandas data frame directly into the hypergraph and then display it inside the hypergraph itself. Again, this is mocked up for purposes of demonstration. So I've got all the different names, I've got the different properties, and I can size the edges and the vertices as well and color code them correspondingly. Okay. So let me conclude with this set of ideas. Remember how we discussed how there's this S distance in hypergraphs parameterized by this minimum intersection size, and I got a collection of all these things that are available. The S-line graph is a new structure we defined. It's where the line graph so in the line graph, I build a new graph with a vertex for every hyperedge, and I connect them with, this is a regular old graph, I just connect them with a graph edge if those two hyperedges intersect, that is, if they're incident. Well, naturally, I can measure the size of that intersection, and I can define an S-line graph to be a line graph where all of those intersections are at least size S. So that's what that notation indicates, the S-line graph. So the one-line graph thereby is just the line graph. Many of the hypernetwork measures that we're talking about, S centrality, S connectivity, and others, can be reduced to the S-line graph, which is obviously a great convenience. Also, from a mathematical, methodological perspective, it indicates that there are certain properties that can be captured by these lower dimensional objects, these two graphs, but others cannot. So random walk clustering, we talked about this need for edge-specific weights, that is cell weights or incidence weights, don't. This is a little illustration of how this S-line graph capability works. So this is, notice that these two very different hypergraphs have exactly the same line graph. And as a general matter by theorem, we know that that can also be true for these higher order line graphs. As the size of S increases, the line graphs thin down. You showing less and less of that structure. I got a few more slides here that illustrate some more of this. So this is a slide about S components. So if I've got an initial hypergraph there like that, if you look at that thing and you say, what's its connectivity? Well, it's connected, right? So we call that a connected component. Well, of course, what I'm going to say is that that means that it's one connected. So this is one, everything is one connected. I've got one giant component. But if I want to ask about the two components, then I end up with this kind of structure. I've actually got 1, 2, 3, 4, 5, 6 two components. These are all of the collections of vertices that are accessible to each other by, within each component, accessible to each other by edge connections of size at least 2. So there's this big meaty thing in the center, this giant component, if you will, but then you'll notice that over here, the IK is its own component because it's only connected by the single vertex I over here and the single vertex K over there. Therefore, edge 13 becomes its own component. Similarly with DH over here and AB up top. Okay, so I'm fracturing my giant one component into a collection of two components. And similarly, as I look at 3 and 4 components, this is a set of 3, 4 components on the right. It looks almost the same, right? You have to squint a little bit and recognize that, in fact, edge 16 over here and edge 17 over here have been merged together because edge 16 and edge 17 are all connected to each other by 4 vertices. So that is my max 3, 4 component, which is 16 union 17. All the others are what we call edge singletons. So these are singleton components, meaning that it's a component containing a single edge. So that's just how that works. Closeness centrality, closeness centrality, harmonic closeness centrality expressed in graphs generalizes to hypergraphs, where now we're using the S parameter. So I stratify the hypergraph basically into collections, all of which are size S or more. And I do the same kind of closeness centrality measure there. Same thing for betweenness centrality. I can generalize that up as well. And I'll just very quickly run through these slides, which basically show that, in fact, in this biological case, we're able to show that there's a lot more, you're capturing a lot more of the gene expressivity in this particular set of genes when you attend to higher orders of S. So if you simply look at a centrality measure on the graph for S equals 1, you're getting what's called enrichment scores in this zone. But as you start to look at 2, 3, 4, 5, you're seeing a 20% increase in the enrichment for betweenness centrality in particular. And so this is just a little example of where, if, at least in this data set, if you're ignoring the higher order interactions that we know are present in these data sets, in this case, it's the gene expressivity against, so what's my incidence matrix? It's the gene expressivity against the different experimental conditions that the human cells were subjected to. It's a virology experiment where you basically infect these lung cells with different things. And there are all these multi-way relationships between the genes that you would be missing if you just did a straightforward CLR analysis. Here is the graph analysis, or an S=1 analysis on that basis. I think that's pretty much what I had. The rest of the notebook here goes on at some length to show, so this is an example of the line graphs inside of HNX. So this is the 1-line graph, the 2-line graph, and the 3-line graph for the little example for Les Miserables that we've been working with all throughout. This notebook is not on the website at the moment, but I can make it available to those who are interested. And as I mentioned, all the tutorials and everything else for HNX is out there now for those who want to play with this. So with that in mind, I will thank you for your attention.